So now with scientific notation, what we're going to do is work together with a numerical value along with a power of 10 like we discussed in that last video. So with the power of 10, we're going to evaluate how we're moving a decimal around. Now this value A has to be between 1 and 10. Now it can equal 1, that's perfectly fine, but it needs to be less than 10, meaning we can go to like 9.99999, like we can go right up to 10, but A can't actually equal 10. So with that, when we determine our value for A, we need to think about those kind of restrictions on our number. So we'll talk about that when we get down here. But first, let's look at a breakdown of how scientific notation helps. And actually, we can kind of get a visual down here where we get these long, complicated numbers, especially something like that. We want to have this notation in order to shorten it, especially if you imagine that if I had 100 zeros there, I wouldn't want to have to write that out on a piece of paper. I want a shorter notation to kind of summarize that value, especially when it's just all of these zeros that are coming through, where those numbers are important. Having the zeros there gives us kind of the scale of the number, but writing it out isn't really necessary. What we need is a way to describe how many zeros we have, and that's where a power of 10 comes through. So let's look at these two numbers here. We're going to look at 4,000, and we're going to look at 0.004. Now 4,000 is exactly the same as 4 times 1,000. So what I did there is I broke it apart into a numerical value along with a power of 10. Because then what I can do is I can rewrite that 1,000 as an exponential form with base 10. I know if I have 3 zeros there, that's going to be an exponent of 3. And this right here is scientific notation. Now, with scientific notation, we typically use a symbol X for multiplication. It's just part of the format of it. However, this is exactly correct too, and you might even find with MyOpenMath it asks for this form every now and then. So you can just use the dot multiplication, but technically writing it, we would write it with an X for multiplication, and like that, and that would be our scientific notation to shorten this number in a way so that we don't have to list zeros at the end. That's covered by this 10 to the power of 3. What you could see here too is that what we did is if you think of the number 4 with a decimal place, like I was saying in that previous video with the power of 10s, with that positive 3, that would tell us to move that decimal to the right 3 spots. So we'd go 1, 2, 3, fill in the blanks with zeros, and there we can see our value of 4,000. So that's where this kind of idea of moving the decimal will come in as well. Now, with this one right here, what we can do is, if we think in a similar way of this would be 4 times, and then this would be 4 times 0.001. So again, changing it to a power of 10, which would be 4 times base 10 to a power of, and again, if it helps, you could think 1, 2, 3. So we moved 3 spots. So this would be a negative 3. Negative 3 right there, which in scientific notation for x, 10 to the negative 3. Again, if we recognize that 4 right there, and the fact that we need a number that's between 1 and 10, so I could see my value of 4 if I imagine 4 with a decimal. To get 0.004, what we would need to do is go 1, 2, 3, and then I'd have 0.004. So that comes from moving the decimal left 3 spots. So with that, we get our negative 3 exponent for our scientific notation. Okay, so let's try this out. So really what we're looking for is kind of this numerical piece, and then we're working with the zeros and this idea of moving a decimal around. So I can see is that 3 and 7 is going to be my numerical piece. Now, often what students will do is write down 37 and then start working on the power of 10. However, this is where that rule becomes important, is that that value over there has to be between 1 and 10. So 37 is not going to work. Instead, what we'll do is we'll put a decimal in there. If you put a decimal right there, 3.7, that works great. So it's kind of like with this number, there's 3 possible locations for that decimal. If we did 37, it would be right there, but that doesn't work. We could put the decimal there, 3.7, awesome, right between 1 and 10. Another spot could be here, 0.37, but that's too small because 1 is kind of our minimum for what A can be. So 0.37 is too small, so we don't want that. Instead, we want that 3.7. So if I have 3.7, and then I'm going to do times 10, so that will just follow right away. Once you determine your numerical part, you'll have times 10, and then we need to figure out the exponent there. And this is where I think about moving around the decimal, because my decimal should end up out here for the number to be 37,000. So what I would need to do is go 1, 2, 3, 4. And then that would get me to the correct location for my decimal. So with this, the movement went right 4 units or right 4 decimal places, which means it's going to be positive 4. And then what you can do is type this into a calculator and make sure that that works. And that should line up that if you type 3.7 times 10 to the 4th power into a calculator, that should give you 37,000. All right, let's look at this next one. So the numerical part is this 96. Again, 96 itself will not work. However, 9.6 is fantastic. So we want to use 9.6 for the numerical part. And then we'll have times 10. And then I just need to figure out my exponent, which, let's see, we're going to be going to the right. And then I'm going to go 1, 2, 3, 4, 5, 6, 7. So that'll be positive 7. Again, with those positive exponents, you're getting these big whole numbers coming out. All right, this one right here, the numerical part, is this 483. So if I have the decimal here, 483, way too big. If the decimal was here, 48.3, that's also too big. That's larger than 10. Here, 4.83, perfect. That's between 1 and 10. So I want to have my decimal right there. So for the numerical part, 4.83. And then we're going to go times base 10. And to figure out the exponent, we're going to be going to the right. And we'll go 1, 2, 3, 4. So that'll be positive 4. So for those, it's just a matter of getting that numerical value that's between 1 and 10, and then figuring out how far you're moving the decimals to the right. Now, when your number is a decimal itself, what's going to change is that our exponent is going to start to be negative here. So I'm going to do the same thing and kind of highlight those numbers. Again, like here would be 52. That's too big. 5.2. That is perfect. So I want to use a 5.2. And then times base 10. And then the idea is that we're going to be moving to the left. So I need to go 1, 2, 3. So we're moving to the left now, which is what makes it negative. So this will be negative 3. For this one, you can see the numerical part's way out here. And 36 is too big, but 3.6 is perfect. So I'm going to have the decimal right there. So I'll have 3.6 for where A is, times base 10. And then we're moving to the left. And we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be a -9 right there. And this last one here, 129, and 129 is too big. 12.9 is also too big, that's larger than 10, but 1.29, perfect. So we're going to use a 1.29 times base 10, and then it just needs to go 1, 2 to the left, so that'll be -2. So with these, you can see if you have decimals coming up here, you're going to have a negative exponent because it's just going to be this difference of moving to the right versus moving to the left. And moving to the right makes these big whole numbers with trailing zeros. And these moving to the left makes these small decimals with a lot of zeros before you see a numerical value. All right, let's go in the other direction of what if you have something given to you in scientific notation and writing it in decimal form. So what we're going to do is I'm going to take that value for A, so that 8.6, and then I just need to translate what the exponent's telling me to do. So -5 means that we need to move to the left 5 units. So I'm going to go 1, 2, 3, 4, 5. So I'll give me my new decimal place, and then wherever you have blanks, we fill in zeros. So this is going to lead to a decimal followed by 4 zeros and then 8, 6. Be sure that with these numbers, I know it can get confusing because we kind of have these 2 decimals. You should only ever have 1 decimal in your solution. So it's the idea that we actually moved it. It was transporting to over there. So it ends up there, and then we no longer have a decimal between the 8 and the 6. All right, with this one, we're going to have the 2.45. And then I just need to read what the exponent's telling me to do. And it wants me to move the decimal to the right, since it's positive. And we're moving to the right 6 units. So we're going to go 1, 2, 3, 4, 5, 6. And then we'll just have zeros wherever we have blanks there. So let's see, we could have a 2, 4, 5 followed by 4 zeros. And then I could just fill in some commas to help me read that number. That should do it. And then this last one here, we're going to have the 1.02. And then I just need to look at the exponent. So since it's negative, we're going to be moving to the left. And we're going 7 units. So we're going to go 1, 2, 3, 4, 5, 6, 7. So we're going to have 6 zeros there and then our number. So 0.2, 3, 4, 5, 6, 102. That's done. Also some notation thing, you can write it just like this. You'll see numbers sometimes with the 0 out front because that makes it a little easier to read to make it clear that there's a decimal right there. They're the same number, so whether or not you include a 0 at the beginning, I'm sure you've noticed I kind of switch back and forth. Either way is fine.